Hello, ladies and gentlemen, and here we are talking about parametric equations. I think this is just about where we left off from last day. And so we're looking here. These are the definitions of parametric equations, remembering that the t value is going to be a variable and it's going to change. It's going to be a member of the real number system, so that is a value that we call parameter, and it allows us to relate x to the parameter and y to the parameter. And notice x and y are no longer related to each other. Okay, so here we go. Example, a line passes through this point and this point. State the parametric equations. Well, just to review a little bit before we get going, we decided that any line can be defined by a particular point on the line and adding scalar multiples of the direction vector. So that's the idea that we've got going on here. The algebra, if I allow the initial point to be x naught, y naught, and I allow the direction vector to be represented by a comma b, we get every single new point on the line will be represented by this equation. So if we were to take the t, which is a scalar, and expand it into the point, it would be ta and tb. And what we would notice is that we would get x comma y equals x naught plus ta comma y naught plus tb, and which gives us the parametric equations of x equals x naught plus at and y equals y naught plus bt. Okay, so let's put in our values that we have. This is our point, so that's the 5 and negative 2. So it's going to be x equals 5 and y equals negative 2. And our direction vector, this is a and this is b. So this will be 2t and this one will be 6t. And those, ladies and gentlemen, are your parametric equations for that line. Remembering that this is x naught, y naught, because that's our point. And this is our direction vector, so that's a comma b. What point on the line will correspond to the parameter t? Well, what that's saying is if we take this line and if we start at point 5 comma negative 2, and if we move 3 direction vectors down, okay, so we move 3 direction vectors down the line, what new point are we at? Well, we can use our parametric equations and just plug it in and come up with an answer. So if my parametric equation says for t, it's going to be 5 plus 2t, and if I move 3 direction vectors down, then that's going to be 3 values of the a value in the direction vector being added to my x, so it's going to be 5 plus 2 times 3, which is x equals 11. And the next one would be y equals negative 2, and it's going to be plus 6t. Y equals negative 2 plus 6 times 3, that's 18. So that's going to be 16. Now it's very early in the morning, so if I'm making a mistake with any of these calculations, please correct it, let me know, and we'll look after that. But anyway, your new point, that is exactly 3 full direction vectors, this size, not smaller, not larger, but this size, down the line from the initial point of 5 comma negative 2 is the new point 11 comma 16. Just to give you an idea of what's really going on here, I want to do a quick sketch just to recap what's happening. So you've got a line, and somewhere this line passes through the point 5 comma negative 2. Let's pretend it's here. That's my initial point, and it has a direction vector of 2 comma 6. So we'll pretend that that's there. Notice I'm not using a scale. So there's 2 comma 6. So my line is actually here. And what we did was we picked this up, and we moved 3 of them. We picked that up, and we moved 3 of them. 1, 2, 3 of them down the line so that we got to the new point 11, 16. Okay? And what's happening there is the reason why we add 3 2's is because we're moving 1 2 for this right triangle from grade 9, another 2, and another 2. So it's 5 plus 2 more plus 2 more plus 2 more gives you 11. And here's your b value. Remember what that is. Remember this was 2, 6. So it's going to be plus 6 plus 6 plus 6. So it's going to be negative 2 plus 18, which gave us our 16. Now, this direction vector, 2, 6, could have been reduced to 1, 3. It would have given us the same direction, but it would have taken more direction vectors to be able to get up to this point. Okay, but it still would work as a direction vector. All right, let's see if I can get some room here. Okay, does the point 1, -8 lie on this line? Well, that's a good question. There's a new point that they're giving us, and they're asking us, does 1, -8 lie on this line? Well, if it does, then I need to be able to get to that point using a certain number of d's. Okay, I need to be able to get from this point using so many d's. So if we look at our parametric equation, for me to be able to get to 1, I can calculate how many d's it's going to take by calculating how many t's it takes. So the 5 comes over, it becomes -4. Divided by 2, it becomes t equals -2. So that's great. If I move -2 direction vectors this way, I will get to an x value of 1. Question is, will I get to the right y value? So we take the -8 and we plug it in. We take the 2 over, it's going to give you -6. We divide both sides, it's going to be t equals -1. That's a problem, because what that means is to get to that point, 1, -8, I need to go -2 direction vectors this way, but I only need to go -1 to be able to get the y value. I need to go 2 for the x value, but only 1 for the y value. We're not going to be lying on this line. The t values have to be the same for any given point on this line. So no, the point 1, -8 does not lie on this line. Okay guys, let's flip over and see what's happening. Find the y-intercept and slope of the line. Now it's part D, so we use all the information from above. So I think we had, what did we have? What did they tell us? They told us that it had a point of 5, -2. They told us that it had a direction vector of 2, 6, and we worked out the parametrics of x equals 5 plus 2t and y equals -2 plus 6t. Okay, so that's all our given information. Let's see if I can focus this a little bit nicer for you. Maybe. All right, so let's see what we can do with this information. It says find the y-intercept. Well, if we think a little bit from grade 9, y-intercepts are where we cross the y-axis. Okay, so if I'm going to cross the y-axis, that means that x has to equal 0. For a y-intercept, x equals 0. Or another way to say that is simply it's going to be 0, unknown, right? Because that unknown's the y-intercept. So I'm going to set x equal to 0 and determine the t value. So 0 equals 5 plus 2t. T is going to equal -5 over 2. Okay, it's a fraction, don't freak out. I have to go not a full length of the d value, but that's okay because remember t is an element of the real numbers, which means fractions and negatives are all good. Otherwise we'd have gaps in our lines, points that we couldn't get to. So I need this number of direction vectors to make my t equal 0. So to get my y value, I would then have to move the same number of direction vectors. So sub into y, parametric. So it's going to be y equals -2 plus 6, -5/2. Okay, so I've got 6 divided by 2, which is 3, so it's -15, 16, 17, so y will equal -17 if I've done everything right. Again, it's early in the morning. If I've made a quick mistake, please fix it and let everyone know. So I see a y-intercept of -17. In other words, it crosses at 0, -17. Then write the equation in the form y equals mx plus b. Okay, looks like it's a throwback to grade 9. We can do this. Next thing I'm going to be interested in is getting its slope. So the slope, need m, which equals slope. Remember that for any direction vector, and again, this isn't memorized, I'm thinking it through, a comma b, this is going to be your rise, and that is going to be your run, so it's a, b. So for any direction vector, your slope is going to be rise over run, b over a. So in this case, our direction vector was 2, 6. So our slope is going to be 6/2 or 3/1, leaving us with the y equals mx plus b of being y equals 3x minus 17. And there we go. So now if you see a grade 9 in the classroom struggling with their homework, go show them how to do it with vectors. That'll really confuse them. All right, so I talked about this the other day. These are just different ways of rearranging the equation. I suggest you get very good at that. Memorizing them is not the best way to go. Being able to move them around using your vector mathematics is definitely the way to go. So we'll flip over there. We've got some examples here to work on. Let's take a look. I'll zoom in a little bit. Okay, determine the vector equation of the line through the point with a direction vector. Okay, so a couple of things here. Maybe I'll go back and just quickly recap something. I always start from the vector equation. The vector equation says a line is given by any point on the line plus a parameter times the direction vector, where t is an element of the real numbers. And yes, you need that. That's important. You're defining what t is. So this is called the vector equation. That's a short form for equation. Another way that the vector equation is written is like this. Another way the vector equation can be written is we change this over here. And the last way you can write the vector equation is you take this point over to the other side. So again, this is a vector equation. They're all vector equations. Why are they vector equations? Because they have a vector in them. This guy's a vector. In reality, this could be a vector too. It's a position vector, but we use it as a point. We bring this over here. And on one of your handout sheets that has homework, you have to work in the vector notation that looks like this. So that again is a vector equation. Why? It's got a vector right there. That's the direction vector. Vector equations, you can use them. So start with x comma y, and it's going to go to x naught, y naught, plus t, a comma b. We can expand that to get our x naught, y naught, plus at, bt, t is an element of the real numbers. This gets expanded to at, comma. And what we can do then is get our parametric equations, which are simply x equals x naught plus at and y equals y naught plus bt. Parametric. Okay. And lastly, if you solve for t in both of them, we're going to get x minus x naught over a equals t. You're going to get y minus y naught over b equals t. And these are called, since t must equal each other for any given point on the line, you get what's called your symmetric equations. Look, Ma, no memorizing. Worked it out. You should do the same. Okay, back to our questions. Determine the vector equation through the point 1, 2 with a direction of. So it wants a vector equation. That's the first thing I'm going to point out to you. So the formula for the vector equation is going to be L equals a particular point plus TD, where t is an element of the real numbers. So it's going to be 1, 2 plus t 3, 1. Ladies and gentlemen, I'm done. That's it. Moving on. Determine the vector and parametric equations. So we want a vector equation and parametric equations of a line through a point, but parallel to this line. Ooh, interesting. So we want the vector equation of a line that's through this point and parallel to this line. Well, if I'm going to be parallel to this line, that means the slopes will be the same. Parallel lines have equal slopes. That's grade 9. We can translate that into grade 12 by saying parallel lines have scalar multiple direction vectors. So direction vector 1 will equal a scalar multiple of direction vector 2. This direction vector is 5, 2. So we're going to use that as our direction vector for our line. Okay? Hope that argument makes sense. We're going through this point. So our equation, p naught plus t times the direction vector, where t is an element of the real numbers, will be 8, negative 6 plus t 5, 2. And parametric equations I can pull right from there with a little bit of help, so can you, or a little bit of practice. So there's my vector, and here's my parametric. We're done. Question. Does the point 14, 11 lie on this line? Well, if it does, then we can get there from the point 8, negative 1 using the same number of direction vectors. In other words, t values must equal. So let's check. So we're going to put 14 equals 8 plus 1t. I'm using the parametrics here. And I'm going to have to work with 11 equals negative 1 plus 2t. So the 8 comes over, so it's going to be 6, I guess. Is that right? And the 1 comes over, it's going to be 12 divided by 2, it's going to be 6. Hey! T values equal. So yes. 14, 11 lies on this line. Yay. Happy faces extra. Okay, one last one. Are the lines represented by the following vector equations coincident? Interesting. Coincident means that they are in fact the same line. They lie right on top of each other. Coincident, the same line. So do these equations represent the same line? Interesting question. We've got two equations. If these equations are going to represent the same line, then a couple of things have to happen. Here's the first thing that I'm going to think about. If R1 is coincident to R2, then direction vector 1 must be equal to a scalar multiple of direction vector 2, meaning they must be parallel. Now that's not the only condition for two lines to be coincident. Here's two lines. They're parallel. They're not coincident. But this is one condition that they need to be. So let's take a look. I would put in the word at least here. So meaning they must be at least parallel. So let's check. Direction vector 1 is going to equal to 2 comma negative 1. Direction vector 2 is going to equal to negative 6 comma 3. Therefore, we can either use the larger one and the smaller one, but let's take a look. You're going to notice that direction vector 1, if I multiply it by negative 3, and if I multiply that by negative 3, they are scalar multiples. So it turns out that direction vector 2 is equal to negative 3 times direction vector 1. If you'd rather, you could say direction vector 1 is equal to 1/3 negative direction vector 2. I really don't care. They both mean the same thing to me. Okay, so they are at least parallel. So let's go back and think about, let's say that again, at least. Therefore, R1 is at least parallel. Now, to be coincident, they need to be shown that they share at least one point in common. Let's take a look at that. Here's two lines. They are at least parallel. If I can show that one of the lines on this line also line up with one of the lines on that line, and they're parallel, then the lines are coincident. So we know 3, 4 lies on line R1. So check if it lies on R2. So taking 3, 4, I'm going to put it into the parametrics of R2. So sub into parametrics of R2. So 3 is going to be equal to the parametrics of this one, which are going to be -9, -6t, and 4, should have used green for these numbers, but that's okay, equals 10 plus 3t. Bring that over, that's going to be 9, 10, 11, 12 divided by -6, t equals -2. Bring that over, that's going to be -6 divided by 3, that's going to be -2. The lines both share the point 3, 4, and they are parallel. Therefore, from here on in, therefore it's going to be done with 3 little dots like that. The lines are coincident. Yay! We finished it.